we'll carry on with today's class. In the previous classes, we have seen a few advancements which happened in operating system after the time sharing. Okay, so we have seen the concept of processes. We have seen the concept of memory management, and I have also asked you to refer the concept of resource management and security. So in this lecture, we'll be actually seeing the developments that has led to other developments, which considerable developments which has led to the modern operating systems. Okay, so these are different from what you have seen. So actually, what you have seen earlier was simply small components or component-wise development which happened in the operating system. Okay, so yeah, process is not a big thing. It is simply a combination of program and data in a different way. Similarly, memory management is not a very big deal when we see from the operating system techniques point of view. So here, what we are going to see is actually a different technique itself for designing the operating system. Okay, so we'll just carry on with that. So let me start maximizing this. Right. So we have seen processes. Process is nothing but it's a collection of data, program, and context. Okay, so combined in a appropriate format, you call them as process. This is, I am revising this because we'll be needing this in the few topics which I am going to discuss today. So there has been a gradual evolution in operating system. As we have seen, this evolution was actually motivated by changes in the hardware, by changes in the software, and a lot of security issues. So when we talk about hardware changes, we have seen high-speed process coming into picture, multi-process coming into picture, and then different kinds of hardware like network and internet cards, which doesn't used to exist earlier, have come into picture now. And then there are a lot of different sizes and varieties of memories, as I have talked about earlier. The pen drives, the flash drives, the cards, the SSD memories, all those things have come up which were not there earlier. So again, so for accommodating all these things, all these changes, the operating system has to evolve. Okay, and then our software point of view, we have seen most of the user applications have moved towards multimedia side. Okay, and client server side. Okay, so when we talk about client server applications, let us say when you're trying to book a ticket for a train or for a flight, you'll be actually visiting to some website, you'll be entering some form. That form actually goes to the server there, it finds out whether the vacancy is there or not. Okay, if there is a vacancy, then the book will seat will be reserved or something like that. So it will, whatever you are actually giving, that is actually a query that is run against a database. So there, the database resides at the server, and that is again controlled by some operating system there. Okay, and therefore these kind of applications have arisen. Okay, in today's life, if we see, we try to inquire about the things, about some services from our home itself. Okay, so we are actually acting like a client, whereas this database is present at a particular location that we call it as server. So even the WhatsApp you use, even the Facebook you use, okay, you are actually a client there. All your data actually is stored in the server, which is owned by Facebook or which is owned by WhatsApp. Okay, so that is why these type of applications have grown today, and therefore operating system also needs to keep itself evolving so that it can keep cope up with these kind of applications. So earlier operating systems would not work that good or would not be efficient in doing this kind of jobs. Okay, so this is another thing driving your operating system, driving the changes in the operating system. And then security also, as I discussed in previous class, there are a lot of, because of internet coming into picture, you have a lot of threats now and then coming to your computers. Every time a new type of threat even the threats are evolving. Okay, even the hackers, they are evolving the way to hack the system itself. So therefore this security also is a very big picture concern, so because of which the operating system needs to be evolved or has evolved in recent days. Yeah. Any question you would like to ask? Sai Kiran. Sai Kiran, you would like to ask any question? You have raised your hand.
No, sir. No, sir.
Okay. Okay. Right. So the rate of change in the demand is such that the adding or modifying existing architecture of OS doesn't work. So every time what was happening is every time a new hardware is coming into picture or any software changes or anything like that is coming into picture, the people are trying to add some extra functionality to the OS. So in this way, what is happening is OS is becoming bulkier and bulkier. So if we assume OS, let us say in the olden days, if this is your memory, let us assume it is 1 GB of memory. So the OS was occupying some like let us say 600 MB of your space. Uh, this was the old, traditional OS. So every time a virus comes in, a new virus is detected, or a new what do you call uh, software or a hardware come into picture, like flash drives, something like that. So in order to support them, some extra functionality gets added. Some extra functionalities get added to the operating system. So the operating system, which was earlier now 600 megabyte, now grows its size and it becomes some 800 megabyte. Let us assume this is just an assumption. So like this, so every time a new what you call evolution comes into the market, either in the form of hardware or threat or either in the form of software demands, so new features keeps on adding in OS. So in this way the OS becomes bulkier and bulkier uh, uh, with every this thing evolution. But again, just by adding these features, we at one point of time they have realized that they cannot actually cope up with the threats and this evolution with the older architecture of operating system just by adding new features to it. Okay, so they have realized that the structure of operating system needs to be reorganized. So therefore the basic operating system, let us say operating system was designed in this particular way. Okay, so they realize that this should not be the design, it should be designed in some other way, or that means the organization of OS itself should change, it should interact in this particular way. Okay, so like this, the changes in the organization they proposed uh, as one of the method in to cope up with this particular threat. So therefore just by adding, this was the addition part, so they have given up this addition part. This the old part they used to remain as it is, and they used to simply add new things. So instead of that, the people have proposed, the researchers they have proposed that instead of doing adding this thing like this, if we just reorganize the system itself or redesign the operating system itself in some other way, it would be better. What you call it would perform better. So with these kind of things came into picture. So therefore they started redesigning the operating system in a new way. So that kind of approaches we are going to see in this particular what you call lecture. So a lot of new approaches or elements of operating system design has been proposed, and this elements, you can see most of the approaches or elements fit in the following category. So whatever the new approaches or the new ways of designing operating system are there, they can actually be classified majorly in these fields which are listed here. Okay, so what are they? Microkernel. One is first microkernel approach, then multi-threading architecture, then symmetric multiprocessing approach, distributed operating system approach, and object-oriented programming approach. Okay, so these are the new proposed what you call architecture, new architectures of OS. They are the completely different design. So whatever OS was designed in a particular way earlier, and these things actually represent a different way of designing the same operating system, so that most some whatever problems we have seen, whatever evolutions we have seen, either in form of hardware, software, and threats, they can be resolved. So we will see that some of these architectures handle software problems or software evolution efficiently. Some of them handle hardware evolution efficiently. Some of handle the threats easily. So that we are going to see in this remaining part of this lecture. Right. So we'll first start with microkernel. Okay. So before we understand microkernel, we need to understand monolithic kernel. Okay. So the kernel which was used, actually what is kernel is, it is the operating system. Okay. we know if this is your main memory, if this is the main memory, okay, so in the main memory, one part will be reserved for operating system, some part of main memory is reserved for operating system, and some part of main memory is reserved for user program. Okay, and there is operating system, some part or main functionality of operating system always resides in this, okay, in this what you call uh, operating system, in the memory. Okay, earlier that used to be called as monitor, but now we call it as kernel. Okay, so kernel is that part of an operating system that which should always be present in the main memory for operating system to work properly. Okay, so earlier the same thing was called as monitor. If you remember the previous days of computers or operating systems, we used to call them as monitor. Now the terminology is changed, we don't call it as monitor, we call it as kernel. So kernel is that part of an operating system, okay, which should permanently reside in the main memory in order to control your computer. Okay, right. So this kernel earlier was called as monolithic kernel. Okay, so what is the meaning of monolithic kernel? Let us understand. So all or most of the OS functionality was provided in the single large kernel. Okay, so monolithic kernel was the one which consisted of all the functionalities which are listed here. So okay, so we know operating system can do scheduling for you. It does IPC. IPC stands for inter-process communication. So when two programs are running, this program also would like to communicate with each other. Okay, so the way of how this program can communicate with each other is called as a IPC. Okay, so there is an element, there is a software element called as a IPC, using which one program can interact with another program. So this scheduling, IPC, file system we have seen earlier, networking, memory management, what you call part of the operating system, device driver part of operating system, and few other things. They were collectively, these all functions were written in a single program or a single process. Okay, so all these functions are written in a single process, and that process resided in this kernel. Okay, so that you called it as monolithic kernel. Okay, so let us just understand what is monolithic kernel in a few more graphical way. So it is nothing more than a process. And what is a process? I said you earlier, process is nothing more than a program. Earlier we used to call it as a program. Later on we combined program and data, we call it as a job. And later on we combine program, data, and the context, and we call it as process. So it is nothing more than a program. Okay, organized in a perfect way, or a better way. So monolithic kernel is simply a program. Okay, actually it is not a program, it should be called as a process, because the concept of program is gone, it is very old. So nowadays we call everything as process. Okay, so it is simply a process, okay, which consists of all the functionalities, where all these different functions of operating systems, the different functionalities of operating function systems are available as different functions. Okay, so when you write an application or when you write a program, obviously your program is going to have a lot of functions. Okay, so the scheduling and all those things, they are implemented as functions in the same process. So this entire thing is a single program or a process, and these are implemented as various functions in that process. Okay, so now imagine a program you are writing where you are having some 100 to 200 functions. So what will be the size of that particular program? Okay, you can imagine that. So that is what is a monolithic kernel. So monolithic kernel is having all the functionalities written as functions, and therefore when you have so many functions, the problem with this will be the monolithic kernel will be very bulkier. So this kernel, if you directly have this kernel in your computer, it may easily occupy more than 1 GB of your space. Okay, it is possible because it is including all the functionalities, not leaving anything behind. Because you cannot leave anything behind, because all of them are encapsulated in a to act like a single program. Okay, so nothing can be left behind. So everything needs to be included. So that is why this monolithic kernel now looks is actually a very bulkier what you call very bulkier in size. So now you can imagine a computer. Let us say if I am using a somewhat old computer where I have just 2 GB of main memory. So this is my main memory, which is my RAM memory of 2 GB. So out of this 2 GB, 1 GB itself is occupied by monolithic kernel, this kernel. Okay. So then what would be the space available to me for user program? Just 1 GB of space. So therefore, if I am having a very low memory, then monolithic kernel is not a good option for me, or it is actually a disadvantage of me, because it eats away most of my memory and I will be left with a very less memory. So with this very less memory, I will be hardly able to accommodate some 2 to 3 programs. So if I have more than, if I try to open a fourth program, then my computer becomes slow. Okay, it will not respond, and all those problems I'm going to get. Okay, so we'll just see that the problems of monolithic kernel and how that can be overcome. Okay, right. So monolithic kernel, you can think of it as a single process with multiple functions. All functions occupy same address space. This will make the kernel bulkier and occupy more memory. Okay, so as we have seen, all these functionalities are implemented as different functions, and they occupy the same address space. So what this address space concept, I think you understand, because we have already seen, that is the reason why I have already discussed the concept of process. So we have seen that in a process, whatever functions are there, or whatever program is there in the process, that can only access the data present here. It cannot access any data which is outside, present outside. Okay, so therefore, for all these functions, if they want data or temporary storage, they can only access this region which is available here. They cannot go beyond this. Okay, so that is why it is written as all functions occupy same address space. So they have only same address space. Okay, and they cannot move outside this. Right. Right. So then what is microkernel? Okay. So the microkernel is actually, you can see it is a trimmed version of the monolithic kernel. So what you do in monolithic kernel is, given a monolithic kernel, you will trim out all the functionalities which are not necessary, and you just keep the functionalities which are very, very important. Okay. So a microkernel assigns only the basic functions to the kernel. Okay. The basic functionality like scheduling and IPC will be present. Okay. So instead of having scheduling, IPC, networking, device driver, everything included in a single process. Now what you do, you remove all the extra things, just keep important things. The important part of operating system is scheduling. Scheduling is very important. After that IPC, after that memory management. Okay, so you just keep those important functions only in the process and remove all other thing, or put all other thing in a different process. Okay, so now you have two processes for your operating system. One very important process or a basic process that you can keep reside in the memory. Okay, that can reside permanently in the memory. Now you can see, because you are including a very less amount of functionality here, obviously the size of the kernel is going to be reduced, and therefore you will be left with more user memory. Okay, then you will ask me a question, so what about the other functionality? We are not getting the other functionality. So let us assume that other functionality is not important to you. Let us say I am trying to load an operating system on an embedded on an embedded device which I have made. Okay, and that embedded device doesn't have an internet connection. So if that embedded device doesn't have an internet connection, do I need networking functions of my operating system? Obviously, they are not going to work, because I don't have a hardware supporting them. So therefore, if I don't have a hardware to supporting them, why would I have them? Why would I have that function in my main memory and let them occupy my memory space, which is again going to be less in my embedded system, because it's an embedded system. Obviously, it is going to have constrained memory. Okay, so therefore, in that kind of way, I can simply remove that functionality, whatever I don't want. Okay, so in this way, you can reduce the size of your kernel. So the microkernel is a type of kernel which only assigns basic function to kernel. And what are the basic functions which are assigned to kernel? Just scheduling and IPC. And these two only occupy same address space. That means these two are present in a single process, and remaining all other functions are available as different processes. Okay, all other functions, again, they are not combined in a different only one process. You may have some tens and some hundreds of different processes for hundreds of different functionalities. Okay, for networking, another process. For file system, another process. Okay, for device driver, another process. So like this, you can have different processes for all those different functions. Okay, these processes, because they are not application, right? These are again operating system related to, these functionalities are related to operating system. Okay, they are not written by user. They are again written by the OS developers only. So therefore, in order to differentiate between a normal user process and this process, okay, so they are actually called as kernel, because they are neither fitting into user application, they are neither fitting into kernel, because my kernel is now trimmed. So therefore, they are given a new name. They are actually called as servers. Okay, as you can see here, servers. They are run in user mode and work as a normal user application. So these servers, which are nothing but the functions of operating system, which are not required, which are not very essential. they actually, when you try to load them, they don't get loaded in the main memory. So generally uh, we know in our main memory there is some area reserved for OS, okay, and there is some area reserved for user program. So what happens is in this OS now you load microkernel instead of loading the previous kernel. In this microkernel architecture, you simply use load the microkernel, okay, and because it is very small, because it is containing only two functionalities, it is going to occupy very less space. Let us assume just 100 MB of your space, okay. So now whenever, let us say if I am loading, now connected a USB drive to my computer, okay. So because that USB drive again, this device drivers will not be available because your kernel is very cut short. So therefore when you connect a USB drive, what should actually happen is the USB functionality of OS should be brought in, okay. So the USB functions, which is nothing but device driver functions of your OS, should be brought into your computer, okay, because they are not available in this main memory. So when this device driver, actually now they are not available as part of the operating system, they are available as a different process. This process is called as server, okay. So when you load this server into the main memory, it doesn't get loaded into the main memory portion or the operating system part of the memory. They get loaded in the user part of the memory. They get loaded here. They act like a user application. Even though they are written by operating system, even though they are part of operating system, they don't do, they are not given the permission to enter into this area. Instead they are loaded into the user program. So device driver now runs in this portion of your memory and behaves like a normal application, but it does its jobs. What is its job? Its job is to understand what is the device connected there and read the data from there and make it available to the operating system, and then operating system can give this data to whichever application is requesting that, okay. So like this the things work. Now you can see operating system. Now the thing is, because if it was part of operating system, then it has to be permanently present here and it would have occupied a larger area. But every time we will not be connecting a USB drive. It is only required when you connect a USB drive. So when you are not connected in a USB drive and we are not using a USB drive, okay, even then you cannot remove that if it is part of monolithic kernel. So now because it is not monolithic, it is a different process in itself. Now when you don't connect any USB drive or when you don't connect any new hardware, there is no requirement of this particular thing, and this thing is simply removed from the main memory, and again you have a larger memory available to you where you can load the user programs, okay, right. So that is what is the advantage of monolithic kernel. We will see few more advantages of monolithic kernel in the other classes, okay. So only basic functionality is included in the kernel. Other functionality is available as other processes called servers. So you can see just scheduling and IPC forms the microkernel here, whereas the other functionality like file system is a different process, device driver is a different process, like this. In the same way, networking is a different process, memory management is a different process, and these different processes, they are actually called as servers, okay. Let us see the features of microkernel. So microkernel, as we have seen with the example, it is very small. You have very small kernel occupying a very less space, okay. And then you can see it decouples kernel and from server process development. Now you have kernel process as a different process, and server as different process. If you just go there in the previous slide, so kernel is a different process, server is a different process. So therefore you can now go and modify this file system. If you don't want any feature here, if you want to modify this function, you can go and modify this function without actually affecting the kernel. So your kernel is going to be saved. Nothing is going to happen here if you go and try something here, if you go and try something here, okay. So that kind of advantage you are going to get with microkernel architecture. Decouples kernel from server process development. Server can be modified without changing the kernel in order to suit application environment, as I just now said. It simplifies implementation. Now your implementation is simplified because you can only include the functionalities that are needed. Okay, first is you include the microkernel, and then whatever functionality, let us say I require device file system, that can be included. So whatever you want, you can selectively include that. Whatever you don't want, you can simply remove that. So in this way, implementation becomes easier. and it increases the flexibility also. Whatever you want, you can keep and you can remove. It helps in the distributed operating system development. Okay, so this distributed operating system development, let us just understand that. So what is distributed operating system is, as I just now said, when you are actually booking a ticket, train ticket, what you actually do, you sit on your computer, you are actually sending a request to a server. Okay, so this server has the database of which train is running where and how many seats are empty there, which seats are booked and all those things. So that is actually present in a server there. Okay, so you are actually sending a query to the server, and server is responding to you whether the seat is available or not, whether you can book or not. So not only you are sitting there, there are thousands of people which are actually accessing this system, and the system is responding to them. So the thousands of clients. So this is client system, what you say, topology. Okay, so not only that, this client system is not only used in trail ticketing and all those things. It is also used in labs and in what you call most of the industries. Okay, for example, in our lab itself. Okay, so we have one computer designated as server. Okay, and this server will have licenses or something like that, and all the user computers, they access this computer to get the license. Okay, so in order to activate some software, for example, Cadence software I'm trying to use, so the license is only hosted on one computer, and different computers simply request the license from this machine, and this machine grants them the license. So in this way, they will be able to, all the machines will be able to access the same single license. Okay, right. So now what happens is, in generally what you can have is these machines which are running here. Okay, you can actually have only microkernel loaded into this, only microkernel loaded into this machine, and this machine will be able to work fine with the microkernel. Okay, and let us assume the second, I just now said that the other functionalities, whatever are there, the only microkernel will be loaded in the what you call main memory, and the other functionalities, whenever you require them, they will be loaded. Okay, so the other processes, when you want file system and all those things, will be loaded here. Now the question is, where is this file system present? Okay, so this file system, if it is not present in main memory, where will it be present? Obviously, as you know, it should be present in secondary storage. So this is actually present in some hard disk of your computer. Okay, so in the hard disk of the computer, this extra functionality will be present, and whenever you want them, it will be loaded from here to here. But in most of the industries, what they do is they actually don't connect this hard disk here, or they will try to use the hard disk of a very minimum size. Okay, instead, all the hard disk or all the features what you require, that will be again stored in the server. So server will have a very huge space, and here is what they will store all the functionalities, and you will not be having the hard disk, or in other words, this function will not be available in local computer, it will be available in the main computer. So now with microkernel, you will be running this, but whenever you connect a pen drive to this particular system, that driver is not there again. So the driver again is not available in the secondary memory also. So therefore that driver now you can get from the server itself. So server, you can copy it into the main memory, and then you can start working. So because this functionality, okay, because this functionality can be needed by all the systems, okay, and it is not important at that particular time. So therefore, all these extra functions or server programs, you can load it in a single computer called, or main computer called a server. Okay, so now at this point of time, you have to actually differentiate between server program and server. When I'm talking about a server process, it actually means it is extra functionality of operating system which is not required to be present in main memory, and they are required whenever they are needed. Okay, and when I say server, it is actually a hardware computer through which a lot of different client computers are responding. So server computer is a different thing, server process is a different thing. Okay, so all this server process, you will load it in this server computer instead of having them in the hard drive. So you will remove hard drive from these computers. Okay, or else you keep the hard drive of a very minimum what you call space in these computers. And if the whatever extra functionality is needed by this particular computer doesn't come from hard drive, instead it comes on internet from the server computer. So in this way, most of the industries, they are actually trying to reduce the what you call the what you call terminal equipment, this end equipment cost, and even then they are and the other thing is they are trying to centralize everything. So everything, all the resources are now here. So if all the programs are here, it is very easy to protect them. They can be easily protected than protecting each and every computer. So in this way, companies are actually trying to protect the things and trying to use the things. Okay. So that is what is distributed operating system. In distributed operating system, what happens? The actual operating system functionality is actually present in the server computer. In the server computer, all all the OS functionality will be present. Whereas on all the terminal computers, just monolithic kernel will be present. Monolithic kernel only, microkernel only will be present. So if they want any extra functionality, let us say if they want networking, then that networking process or networking server process, it gets loaded into this main memory, but it doesn't get loaded from hard drive here. It gets loaded through internet into this particular memory area, and this computer will be able to work. So this is called as distributed operating system, because operating system is not residing in a single computer. It is actually residing in a server computer, and hundreds of different terminal computers are able to access the operating system which is stored in a single computer. So that is what is distributed operating system. Right. So now let us understand another concept of operating system, or another approach, a new way of designing operating system, which is called as multi-threading. Okay, so multi-threading is a technique in which a process of an application is divided into multiple threads that can run concurrently. Okay, so generally what happens is, as we have seen, we have actually divided an OS, okay, into lot of processes. A given OS was divided into processes. So these processes you called it as server program 1, server program 2, and the main important process you call it as microkernel. Okay, so a single operating system is divided into multiple processes. Not only operating system, even an application. Let us say if I talk about some application like Microsoft Excel. Okay, so even that application is also divided into processes, but this time these are user process 1, user process 2, user process 3. Okay, so that functionality can be added whenever they are needed. For example, if I am using an Excel, okay, let us say there is an insert option. I will always not be using the insert option now and then. Okay, so that the insert option is required whenever I want to insert some what you call links there, or some diagrams there, or something like that. Okay, so that insert will be implemented as a different process. Okay, similarly, let us say the drawing, you can have another options. Let us say filtering options, that also I will not be using now and then. It will be used whenever I use filtering. So even that will be written as a different process. Now the entering the data and formulas, that can be actually written as a different process. So now this application Excel, for example, is a set of all these different options, processes. Now this process can further be a process is can be further divided into what are called as threads. So given a process, you can divide a process into multiple threads. Okay, so that is what is called as multiple threading. Multiple threading is a technique in which a process of an application is divided into multiple threads that can run concurrently. And what is important thing about these threads is they can run in parallel. Okay, let me just understand about that in a short while. So what is a definition of thread? If you want, thread is simply a part of the process, but the thing is, it is a dispatchable unit, a dispatchable unit of work that has its own data areas, its own processor context, and which is interruptible. This is what is the meaning of thread. Okay, and what is process? If you see from multi-threading point of view, process is simply, it is a collection of more than one thread corresponding to a system resource. Okay, or this definition of process we already know. It is the program under execution. So process is program under execution, and seen from multi-threading angle, it is simply a collection of multiple threads. Right. We will understand this with one example here. Uh, let us say I have a program. Let me write a program here. Okay. Let me just. Okay, so if I have written, let us say a is equal to 10, b is equal to 20, c is equal to 30, okay, d is equal to 40, okay, c is equal to a plus b, or some f5, e is equal to a plus b, and right, some g is equal to c into d. In a normal computer, what happens is this program is run step by step. So first this gets executed, then 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 this gets executed. So how many cycles you require? 1, 2, 3, 4, 5. Okay. So you have given a time. So in the first cycle, you are allotting A. In the second cycle, you are allotting some value to B, then C, then D, then you're calculating E, then you're calculating G. Let us assume at the same time after this, uh, I want to read some input. So read file, I am reading some file here, okay, and then I want to just print the results, E comma, I want to print the result E, okay. So this I am trying to do, let us assume. Okay, so then this reading happens here in this cycle, then printing happens in this cycle. So 1, 2, 3, 4, 5, 8 cycle it requires for my job to get completed. Now if you can just see this program, there are some things which you need not do in parallel. Okay, for example, a is equal to 10, b is equal to 20, okay, that is right, that is this instruction, and this instruction. You can see this instruction is not dependent on earlier, this instruction, this is not dependent on earlier, this is dependent on this, and then this instruction is dependent on this. So all those related instruction, if I can just put them in a single what do you call place, then this program is actually a part of this program, but it is actually not related to other instructions which are present here. It has because this part you're actually taking a, b, you're adding that and printing, it has nothing to do with the other things which you are doing here. You're multiplying and you're reading file, but that has nothing to do with this particular thing. So this is actually one unit of work. So, and similarly you can have another unit of work in the another what you call part of your program. What you are actually doing, you're allotting C with some value, okay, D with some value, and you are printing that, right? So this has nothing to do with this, okay. Both of them are not related. If you can see, they are not they are mutually exclusive to each other, they have nothing in common, okay. Similarly, the other function, that is a read file, this is also not related, okay. This program, given this program, I am able to break down this program into mutually exclusive parts, okay. And you can see when I run this part, it is not compulsory. Even you run the earlier application, they were actually happening in sequence. Actually, it is not compulsory for this program to run in sequence. So, but this thing should run in sequence. You can see this part, if it doesn't run in sequence, let us say E is equal to A plus B happens before you declare A and B, then E will get a garbage value. So therefore, this should be done in sequence, okay. And it is not compulsory that after E you have to calculate G and all those things. So even if you calculate G some other point of time also, it will not have any impact on this part of the program. So same program, I can break down into a different sequence such that they produce the same result. So if I break down in these 3 units also, and they run this after this after this, even then I will get the same result. Okay, why? Because they were mutually exclusive to this. So therefore, this program, which this, if this is a process, then I can write this process as 3 different threads. Okay, so now I can have 3 different threads. So now what is the advantage of this particular thing is, Advantage of this particular thing is, you know, in the multiprocessing system, the system of your computer actually does scheduling of processes. So it does one process, then after some time it switches to another process, after some time it switches to another process, like this. Okay, so if you have, instead of processes, if you have threads, then you can do switching between threads also. I can do this thread 1 switching, okay, the thread 2 switching. So this can be T1, this can be, I can now give to T2, now I can give to T3. If it is taking a time, then again I will go for T1 and T2. Okay, so because these threads they are much more minute and their context is very much small when compared to process, switching between threads is very easy when compared to switching between processes. Okay, so in multi-processing, you switch between process, whereas in multi-threading, you switch between threads. Okay, you run this particular thread. Okay, after some time you stop the, let us say after this instruction, you stop this thread, then this thread will be run. This after these two instruction, it will be stopped, then this will be run. Let us say this is an IO instruction, it takes time, so therefore because it is taking time, it will be stopped and chance will be given to this. So it runs and it prints. Okay, if printing is taking long time, it will give the chance to this to run, so it gets completed. Again, it will give a chance to this. Again, it is taking a time. Again, you will come back and print it. So in this way, you have increased the efficiency. Here, if this was happening in sequence, then while reading the file, it would have slowed down your system. This printing was not possible while you were reading the file. Okay, and this the same because now everything is happening in parallel. If printing is done faster, then printing will happen faster, and this will get delayed. So this will not stop this. So your process in turn will complete in a shorter time. Okay, if you do multi-threading. So that is what is multi-threading. Multi-threading, you know, multi-processing was to switch between process. Multi-threading is to switch between threads. But before you switch between threads, you have to create the threads. And how do you create the thread? You can create the thread by encapsulating mutually exclusive part in a given program into different tasks. So this is your task. This is one task, this is another task, this is another task. You have to encapsulate into tasks, and then you have to run. Then you may think that this is a very complicated process. How can I find all those things? This program was simple, so I am able to do it. So if it's a complex program, how to do this? Actually, you don't do this. The compiler itself is designed so that it can identify the common part and it can form them into different threads. So there are modern compilers available which can do this for you. Okay. Right, so that is what is thread and process, and that is what is their distinction. Okay, let us just move on. I hope you have understood multi-threading with this example. Multi-threading combined with some other thing becomes huge, what you call advantage. We will see that later. So multi-threading, it is helpful when application contain a lot of tasks that are independent and can run in parallel. Example is database server. Database server is a very good example because in database server, the queries will be coming from a lot of different users. So one user will be coming here, one user will be coming here, and this query will be to read the data. Okay, in database, you actually read data, write data, update data, something you will do it. Okay, or you delete the data. So because all these tasks are mutually exclusive to each other, so all this, the operating system which is running on this database server, it can actually switch between these tasks. It can do multi-threading here. Right. So now let us move on to the another technique of operating system design, a new approach to operating system design, which is called as symmetric multiprocessing. So symmetric, it is a term that refers to computer hardware architecture and operating system features that exploit the architecture. Okay. So the symmetric multiprocessing actually comes into picture when you are actually talking about multiprocessor system. Now, if we talk about the modern computer chips, so modern processors, they don't come with a single core. Now you have multiple cores, either 4 core or 8 core or something like that. Okay, so that means there are 8 copies of the same processor available in the memory. Okay, so now 8 copies of processors you are having in the same chip. Okay, so that is what is called as multiprocessing or multi-threading. So therefore, if you give one program, that means here the problem is you don't have a single program that you have to utilize. Now you have multiple programs available, multiple processors available. Now operating system can utilize this in multiple ways. Okay, so now you can design one operating system such that this processor runs only with one processor, runs process 1, this runs process 2, this processor runs process 3, this processor runs process 4, and all of them are running these things in parallel. So when all these processors are running in parallel, so instead of process 1 happening instead of you switching between process 1, then process 2, then process 3. Okay, so like this, you're switching between one another. You've given a single process in a single process system. So instead of doing this, what will happen here in multiprocessor? Process 1 will complete, and on first core, simultaneously process 2 will complete on second core. Similarly, process 3 will complete on third core. So in this way, all these things complete in a very short span of time, which would have taken a very long eternity till here. It is now completed in a time which is from here to here. Okay, why? Because all these multiple people are working together. It is very difficult than saying here. Okay, we may say it is like this and we may understand it good, but there are a lot of problems, because two processes might be using the same resource, because processor having multiple processor is not enough. Let us say if you have a single printer and process 1, 2, 3, all of them want printer, then in that scenario, even if you try to do the process on multiple machine, it will not be giving you that much benefit, because all of them have to wait until process 1 finishes printing. The process 2 has to wait, process 2 finishes printing, process 3 has to wait. So imagining a situation where they don't require these resources, and that situation, multiprocessing, that means SMP, symmetric multiprocessing, that means giving different codes, different processes to execute, and if they execute in that particular way, you will get a very good benefit. Assuming ideal cases, they don't require common resource. If they require common resource, then this benefit will be reduced to some extent, okay, or some more time they are going to take to execute. Now, as you can understand, the symmetric. Okay, first we will understand what is this word symmetric. Symmetric means all these core are capable of doing the same operation. If this is able to add, subtract, multiply, all of them will be able to add, subtract, multiply. Okay, that is the meaning of symmetric. In most of the system, you have two cores, but one core is meant for integer, other code will be meant for floating point unit. Like this, some difference will be there. So when you say symmetric, that means all of them are same and they are able to do the same job. Right. So that is what. Okay, so once you have multiple core, advantage would be multiple processes. Each process you can assign to one core, and in that way you can save the memory. And if you are implementing multi-threading, if you remember the previous topic of multi-threading, we have divided one process into a lot of different threads. So in that way, you can give threads here. So in the previous program, if I just go to my previous program, yeah, if I just go, okay, I've deleted that. So if I just go to the previous program, so in the previous program, what was that? We have one program we have actually divided into 3 threads, if you remember, thread 1, thread 2, and thread 3. So now thread 1 you can assign to one processor, thread 2 you can assign to another processor, thread 3 you can assign to third processor. In this way, this complete process will be able to finish quickly. Okay, so that is again a problem. You see, again another advantage. So once you have multiple cores, you can either assign each core with different processes, or you can either assign each core with different threads. Now, imagining that you have 8 processors, okay, or 8 cores, but given programs are 16, then each processor will have to switch between two programs. Then in that case, you will allow two processes, process 1, process 2, two same process, and then switching or scheduling happens, multiprocessing happens between process 1 and process 2 on this core. Then if process 3 and process 4 are allotted to this particular core, then operating system has to switch between 3 and 4 for this particular core. So in this way, operating system job also increases when you have symmetric multiprocessing. Okay, if you have lesser number of processes compared to the core, it is an advantage. You will be able to do it. When you have more number of processes when compared to core, then operating system has to do a lot of job, scheduling each processes on each core. Yeah. So there are a lot of advantages of SMP. SMP provides you advantage in performance. Just now we have seen the job which would have taken a very long time on a single processor completes very quickly on multi-core processor, because all of them are running in parallel. Okay. So then you have other advantages of availability, incremental growth, and scaling. Okay. So first we will understand the performance of advantage. You have already understood. If it's a single core, it would have taken for the processor to complete all the, let us say, 4 to 5 processes if we are given. So in order to complete that 5 processes, it would have taken this much long time. Whereas if in in multi-core process, because all these processes are running simultaneously, so all of them gets completed on their respective processor within a short span of time. So obviously you will save this much time you are going to save. Okay, so this is one advantage when compared to performance. And as I said you earlier, this performance is an ideal case when resources are mutually exclusive. Now the question is of availability. Availability is a very good advantage. Okay, so let us say if you have 8 core, okay, and you have used this 8 core system in some Mars mission. Okay, so you have made some Mars robot based on this particular 8 core processor. You have sent this robot to Mars. Now, okay, so before we send this, let us say there was a single processor. So you have made some robot using a single core processor. Now in this case, you have made some robot using a multi-core processor. Okay, this robot you are sending to Mars. After you send to Mars, you find out that on the second day, this processor failed. Okay, so if the processor fails on the second day after you launched it onto the Mars, okay, the whole complete thousands of dollars which you have spent goes wasted. Okay, because this processor is not working. Now imagine the same situation. You have done the same thing with multi-core processor, and after going to that Mars, again one of the processor fails. If one of the processor fails also, it is not a big problem because you have the remaining 7 processors available. So your mission is not a fail. It's again a success. But the only problem is this: now the 7 processor has to do the job what 8 processors has to do. Okay, so that is what is the advantage of availability. So if you are using symmetric multiprocessing, then even if some core fails, you will be having another what you call cores available to you. But in order to utilize this available cores, operating system needs to be intelligent. Let us say this process, this core was handling the task 1 and 2, this was handling 2, 3, 4, 5, 6, 7. So like, similarly, this process was handling the task number 11 and 12. Okay, so when this process fails, this 11 and 12 can no more be executed on this particular core. So therefore, operating system needs to be intelligent enough to move this task from here, core, this what you call damaged core into some other core. If the operating system is unable to do this, then again your system or your complete experiment is a flop. So therefore, operating system also needs to be designed in such a way that it understands that something has gone failures or some what you call core has failed, and it should be capable of what you call transferring that particular program into some other core, or in other words, utilize the remaining cores. It should be capable of adjusting. Operating system should be capable of adjusting itself if you want to have this advantage of availability using SMP. Now incremental growth. Incremental growth is the operating system should be designed, SMP is designed in such a way that if you are using 4 processor, then it works what you call according to this 4 processors, it will try to utilize 4 processors in a better way. So at some point of time, if the user replaces this 4 core processor with some 8 core processor, then the SMP will automatically adjust itself so and distribute the work on these 8 processors, so that ultimately the performance will be improved. Okay, or the user will be able to see the effect on his screen. Okay, so that is what SMP means. So if SMP is intelligent enough to customize itself based on available number of cores, that is so given that way. So if user has some so let us say if I have financially that means a lot of money now, then I can go and buy a higher end processor. Just processor I need to buy, operating system same way is going to work for me, and it is going to utilize that particular thing. So that is what is an advantage of SMP. An ultimate thing is scaling. As I just now said, you can scale it, you can change any number of processors. It is similar to in incremental growth. Above advantages, as I said, are potential. It can be combined with SMP for thread level parallelism also. We have seen this. Above advantages are just potential advantages. They are not real advantages. Real advantages you will have if you are not having resource conflict. So if you are having resource conflict or resource dependence, this is not going to work. Now let us move on to the another concept, which is virtualization. Okay. So generally, what happens is our applications run on operating system, and operating system we install on your laptop or on your machine. Okay. For example, I am having this laptop. On this laptop in Windows installed, and on this Windows I am able to use the Zoom app or my Microsoft Word app. Similarly, so therefore apps depend on operating system. Operating system again depends on the computer. Okay, is installed on the computer. And any computer traditionally, I'm not talking about today's technology. If you just go a few years back, any computer or PC was able to run only a single operating system at a time. Okay, even now also to some extent it is valid. So if I am using, if I decide to put what you say a Windows operating system on my laptop, then some of the applications which are meant for Linux I will not be able to use. For example, there is an application called as Vimedit. Vimedit is an editor for Linux. Okay, so if I try to use Vimedit on my this application, I will not be able to use this because Windows doesn't support Vimedit. That application is what you call legacy application of Linux. So I need to install Linux if I have to use them. Same is valid for Microsoft Word also. If I want to use Microsoft Word, I will not be able to use on my Linux machine. Okay, because Microsoft Word is proprietary of Windows. So if you want to use Microsoft Word, you have to install Microsoft operating system. So therefore, on the Linux machine, I will not be able to use Microsoft Word, and on my Windows machine or on my Windows operating system, I will not be able to use Vimedit. Okay, so these are the problems. But my intention is I want to run both the applications on my computer. Okay, so if you want that to happen, then you have to use a concept called as virtualization. Okay, so you have to use virtualization to have both the legacy applications on your machine, where both these legacy applications are actually running on two different operating systems. So what does it actually mean? It actually means that I should be capable of running two different operating systems simultaneously on my machine, which is actually quite impossible. You cannot have two different operating systems running on the same machine. But in order to provide an illusion that you are actually running two different operating systems simultaneously, a concept called as virtualization is used. Okay, so what is this virtualization? So how virtualization actually works is, let us say this is your computer, and in my computer I have already installed Windows. Windows will now be my host operating system. So on this host operating system, what I can do is I can install a virtual machine monitor. VMM is what you call again a software program which you need to install. So that VMM, what it does is it allows you to have a virtual operating system on top of this another virtual operating system. For example, I can have a Linux what you call virtual machine installed here. I can have some other operating systems virtual machine installed here. So once I have virtual machine installed here, again let us say I have some Android virtual machine installed here. Okay, so if I have this virtual machines installed, okay, so they are actually like acting like virtual Linux operating system. So once I have a Linux operating system, it's original or real, then I will be able to run its legacy application. In my case, I was actually talking about Vimedit. Okay, so similarly, if I have Android, I will be able to do Android related applications, any legacy application of Android. If let us say if I talk about Play Store. Okay, so like this I will be able to use all these applications. Even though these applications are dependent on different operating system, I will be able to use them on the same machine. You can see this is my same PC or my same laptop, and all these legacy applications I'm able to run. Okay, so for this a concept called as virtual, you need to install this software called as VMM. So what this VMM actually does is, when you write an application, when someone writes an application, we have seen in the computer user interface, applications are actually run on operating system. Okay, through libraries. Okay, they run on operating system. The operating system in turn runs on your hardware. Okay, and you call this interface between operating system and hardware, the interface is called as instruction set interface. Between library and operating system, you call it as application binary interface, ABI. Okay, ABI. And between application and library, you have what is called as API. Okay, so what this virtual machine actually does is, you can see when this library is interacting with OS, it actually interacts with an ABI. So therefore, this application actually interacts with this using some ABI or API. Let us say if it is using library, it will have API. If it is not using library, it will have ABI. Okay, so API or API it will use and it will interact with this. This API or ABI is understood by this particular operating system. In this case, we have assumed this to be Linux operating system. Okay, so now this operating system, this VMM, what it does is it changes this API or this ABI. It maps this ABI or API to the ABI or API of host operating system. It is simply mapping one function call to another function call present in this operating system. That is what it does. It changes this API of Linux into ABI or API of host operating system. That is what is the job of this virtual machine monitor. Okay, so because it is just, it can simply change link one program to another program. So in this way, like a lot of different operating systems you can have, you have to simply map their APIs and ABIs to the existing APIs and ABIs in order to simply run their applications. So that is what happens in any virtual machine. Okay, so and that is why I have stressed on these interfaces while I was discussing the your first topic. Okay, right, this can be better understood. Now if you just see, just give me some 2 minutes, I'll just explain this. So if you can see the advancement with the languages, we know we used to actually write in machine language, okay, which was ones and zeros. Okay, then people came up with another type of language which is called as assembly language. Okay, where they use mnemonics, like which were understood by humans, like move, add, and all those things. Okay, what was the motivation, what was the advantage for going for a machine language to assembly? Because this was, you cannot, as a human you cannot remember this you as a human you can remember this. But the problem with this assembly was, let us say if they have two different processors, if I have processor 1 and processor 2, processor 1 will follow different assembly language, it will have assembly 1, it will follow different assembly language. So therefore the same program, let us say if I am writing the program for array multiplication, I need to write differently for this processor, I need to write differently for this processor, because their instruction sets are different. So therefore people don't want to write the same array multiplication program again and again for different language. So what they have done, they have developed what is called as high level language. Okay, so high level language, for example C. So if you can write the code in C, it will work on this processor and it will work on this processor. Okay, so how was it possible? Because they have used compilers. Okay, so actually these processors were running operating systems, and operating system has some compilers with them. They had their own compilers. So therefore when you give this C program to this operating system, the compiler in this operating system maps it to this particular processor. Similarly, when you give this C program to this operating system, it maps it to this particular processor. So let us say this operating system was again the same thing, Windows. Here also it was Windows. Okay, so you know different architectures are supported by. You can have same operating system running on different architectures. So therefore, you have same operating system. So unless and until your operating system changes, you need not change your program. The same program is going to work. But if you have different operating system, let us say irrespective of processors. Now, if I have OS 1, okay, here I have OS 2. Okay, so if I give the same program to this OS 1, this to this OS 2, in this it may run, in this it may not run, because their compilers are different. Okay, so therefore for this to happen, if you, that means if you want the program to run on all this machine, the fourth generation of languages came into picture. Okay, the fourth generation, which you have Java and all those things, Java or .NET and all those things. This Java and .NET, how they are able to run on different operating system is they use this concept of virtual machine. Okay, so if you are familiar with the Java, you will know what is the meaning of a JVM. Okay, so before running a Java, you install what is called as a JVM. Okay, what is JVM? Java virtual machine. Okay, it is a virtual machine. Okay, so therefore you give the program in Java to this particular machine. So it, instead of going to OS, it goes to the virtual machine, and virtual machine translates the API to this particular OS one. So when you want to run the same Java application to Linux, you give it, you don't give it to operating system, you give it to the JVM running on Linux, and this JVM will convert this API or API into the API or API of this particular operating system. So that is the reason why if you write in Java, your application will be able to run both on your Windows as well as on your Linux. And same is the case with all the fourth generation languages. So fourth generation languages provides you portability across all the different operating system. And how do they do it? They actually do it using virtual machine concept. Okay, right. So similarly, you can not only have virtual machine for supporting one particular language, you can have virtual machines supporting different operating system also, mapping one operating system to another operating system, as I have discussed in earlier examples. So you can have a virtual machine for mapping Android to Windows, you can have virtual machine for mapping Linux to Windows. So like this, you can have different virtual machines. So there are companies like VMware which produces a lot of different virtual machines. You can just go and explore that for more this thing. So yeah, once again. So same JVM is actually an example of virtual machine. So we will see the architectures of the virtual machine in the next class. Right. So now you can again post your attendance for your final this thing, and we'll end our lecture here. In the next lecture, we will talk about the different architectures of virtual machine, and then we'll move on to the next topic. I have already taken a lot of time, so that is why I'm not giving you tests, even though I have it. I will probably give it in the next class. Yeah, if everyone has given the attendance, then I can end the meeting. Yeah, I am ending the meeting now. Thank you, everyone.